Okay, so it's a great pleasure to have Takis Kontos from ENS Paris, who's going to talk to us today about experimental tests of the theory of the AC Kondo problem.
Okay, thank you very much. So thanks to the organizers, Manas, in particular for the invitation in this marvelous place. So I'm really happy to be back here. That's a very nice conference. So today I'm going to talk about an experimental work done by mainly Laure Bruat and Matthew Desjardins within the hybrid quantum circuits team, so which is here. And in fact, there are newcomers in the team. There is Zaki Lektas, François Mallet, and also Matthew Delbecq. But this work was somehow done before these guys came, and it was at that time Jérémy Viennot, also Matthew Dartiaille as well. And on the theory side, we have benefited from the long-standing collaboration with Audrey Cotet. And also for the last part, I'm going to show numerical renormalization group plots from Min-Chul Lee and Man-Soo Choi from Korea. So, so the main, let's say, topic of research, like in this work, is Kondo physics. And Kondo physics is a pretty old subject already, but there is still a lot of surprises related to this very important condensed matter topic. So it was first, discovered in magnetic alloys. So for example, in copper, if you put 0.2% of iron in copper, and you measure the resistivity as a function of temperature, you see that the resistivity increases at some characteristic temperature, which is called the Kondo temperature. This, in fact, increase of resistance in the magnetic alloys, even though it was found as early as the 1930s, was only explained in the 1960s by, the first explanation was Kondo, and then it was also one of the big successes of the renormalization group to explain these features. And so the idea is that in these magnetic alloys, this increase of resistance is related to the screening of which occurs at low temperatures of the dilute magnetic impurities by the conduction electrons in the host matrix, and this is why it slows down the conduction electrons, and then in turn have this increase of resistance. And but thanks to nanotechnology, there's been a revival in the let's say late 90s of Kondo physics. And it has been shown, for example, in these three nice examples, that that's a generic property of any localized electronic state coupled to a continuum of electronic states. So as soon as you have, for example, a spin degenerate state, or even it can be like other kind of degeneracies, coupled to continuum of electronic states, for example, in C60, in carbon nanotubes, semi-conducting quantum dots, or like here, or magnetic add atoms also on cobalt and copper 111, you run into this kind of physics because in fact these localized electronic states can play the role of a magnetic impurity, and this has allowed a direct investigation of Kondo resonance with exquisite details, and especially at low frequencies. And so far, mostly people have measured the conductance through these kind of systems, either if you do a thermal spectroscopy experiment or you're measuring transport in these two mesoscopic systems. And the question which I will try to ask today is what happens when one shines light at the single impurity level? So you can shine light, you can use light for two things, as you will see. Either you shine light to induce an out of equilibrium transition, an out of equilibrium dynamical state of this impurity, and you see what happens, or you shine light in order to probe the electronic system, and you will see that both these ways of shining light can be interesting to understand interesting features of the Kondo physics. Okay, and let's say the reason why, any localized electronic level can essentially be mapped onto a Kondo problem to some extent is actually shown here. it can be essentially shown that if you have a strong, Coulomb repulsion on a single electronic site, and this electronic site is coupled to electronic continua, this is the naturally leads to the appearance of a magnetic moment coming from the impaired electron. So this way of modeling the physics is actually the Anderson model for magnetic impurity. And although, it's like maybe the simplest model what I can think of a magnetic impurity, and this can be mapped onto a Kondo problem, it's actually a many-body problem, so it cannot be solved, let's say, in all the parameter space, and it's essentially the simplest many-body problem one can think of, and its physics is relevant for many condensed matter systems, so it serves as a test bench for more complex theories. And this is why, it's so interesting also to study this in details, and this is also why it's interesting to study the dynamic aspects of this kind of problem, because we are going to learn possibly dynamic aspects into more complex, strongly correlated systems. Okay, and so in order to see, what kind of interesting physics can occur when you mix Coulomb interaction and spin physics, I have sketched here some of the basic processes which are actually at work in Kondo physics and give rise to this many-body resonance, which is called also the Kondo resonance or the Abrikosov-Soule-Nagausa resonance. So imagine you start with a situation where one of the Fermices is filled with a downspin and there is an upspin on a localized state. Essentially, we have two possible virial states which are occurred quantum mechanically. Either you empty this state or you fill it with another charge. And essentially, when you look at the final state in which you can enter from these two virial states, you see that there are particularly interesting states which happen where essentially you have flipped the spin. And since the spin is assumed to be degenerate in that case, this is essential. Do you have a question? Okay, you're doing this. Be careful, because if you do this, I can assume that you have a question, and therefore this can be dangerous sometimes. But mostly for mostly for the students. So they don't want to ask questions, and this is why I say it can be dangerous sometimes. For colleagues, of course, it's never dangerous, no harm. So let's say, so then there is a downspin, and so they have the same energy. But what you see is that you have flipped the spin, whereas the charge is with exactly the same between initial and final state. And so this means that you have decoupled essentially the spin and the charge degrees of freedom, which is completely different from what you would have from a resonance level. And in fact, when you sum up all these processes and take into account that you have a Fermi, let's say C here, this leads, when you to this many-body resonance called the Kondo resonance. And what you see here is that since you have transferred the charge from here to there, this kind of process will naturally contribute to the conductance of the system. Although, it corresponds to a frozen charge, since the charge has not changed from here to there. So this kind of freezing of charge, whereas the spin is free to move, that's something which is really which arises because you have a correlated transport. And so this, I will show you that by shining light, you can see directly this phenomenon. And of course, the natural thing to ask to ourselves is that now, of course, this kind of finite conductance arising from this kind of processes will be revealed when you bias this system, when you have a tiny bias, a DC bias from here to there. And now the question is, what happens when you perturb very strongly the system, when you drive with a large bias, and when the frequency of this bias is high, comparable to this to the width of the many-body resonance, which is called the Kondo resonance. This is now what I'm going to explain you now. Now we have in fact done an experiment which allows to unravel what happens in this situation. Okay, so this is two kinds of experiments which I'm going to talk to you about. So the case of the very strong AC drive of a Kondo resonance. And then for the last part, I will show you how you can use like photons, but photons trapped into a microwave cavity to do a readout of this peculiar many-body system. And this will essentially make contact to what Mike told us in the morning, but in a slightly different context. Okay, so let's start with this first topic. And in fact, now what we're going to study is essentially the current at low frequency flowing through the system when we have a large microwave power applied to the source and the drain of the system at high frequency comparable to the Kondo temperature. So this, in fact, is the usual photon-assisted tunneling setup. So essentially, there are many works devoted to this problem for quantum dot circuits. And following these works of quantum dot circuits, there are many theory works devoted to this problem in the Kondo regime. And essentially, so it's a non-exhaustive list of works which we have found, in the literature. And why it's interesting is because essentially we have a competing mechanism between the large frequency comparable to the Kondo temperature and the formation of what is called sometimes the Kondo cloud, which is this many-body state between the spin trapped on the island and the spins in the conduction electrons. And I have picked up a particularly illuminating paper by Kaminsky, Nazarov, and Glassman, which show that although the problem is a priori complex, there is some universality behind it, and it's related to the usual universality which one has in Kondo physics, and essentially because although you have many body problem, this is a many body problem with many possible complex excitations in the problem. At low energy, everything boils down to a single energy scale, which is the Kondo temperature. And in this theory paper, this is exactly what they worked out. They have shown that there is also the same thing holds for the AC transport. So essentially, everything should be scaled by, let's say, the Kondo temperature, either the microwave amplitude of the AC drive or the frequency of the AC drive. And so generally, the physics expected is that you will have some microwave-induced decoherence, but there will be a universal response as a function of the frequency normalized by Tk and the amplitude normalized by Tk. So there is one counterintuitive prediction, which actually we're going to study experimentally, is that the larger the frequency of the AC drive, the higher the Kondo resonance will be. So the lower you will have a lower effect at high frequency when you for a given amplitude of excitation, which is kind of counterintuitive because one would expect that the higher the energy of the photon, the higher the effect on the Kondo cloud will be. Okay, so let's now do the experiment and try to test these ideas. And before doing that, I would like to put in context our work and of course, to show you that we're not the only one to perform this kind of experiment. So there were actually two experiments, essentially, one done by the Delft group and one done by the group of Kogan, and where essentially they investigate this. And so what they saw essentially is that when you shine power, essentially, the central Kondo peak is completely quenched. So this you see that when you increase the power, the Kondo peak is lowered and broadened, and so that's one thing. And in addition to that, sometimes, but this was a bit controversial at that time between these two experiments, you also observe satellite peaks. So besides this kind of the reduction of the Kondo peak, you observe satellite peaks which are exactly at the frequency of the photons. And this is also reminiscent of photon-assisted tunneling. But here, since you have, let's say, some interplay between decoherence on this many-body state and this photon-assisted tunneling phenomenon, you see only two satellite peaks. So this was more observed here. But no study of universality was done at that time for these works. because essentially, already, I mean, some simple things were completely inconsistent between the various experiments. So there's another work also done by the group of Kogan, more recently, where actually they could study how the microwave-induced decoherence seems to, I mean, can be related or not to the Kondo temperature. And it seems that, in fact, this is related to Kondo temperature. But you see that what they saw, I mean, for example, the frequency dependence is that there was some kind of non-monotonic behavior of the peak as a function of the frequency. And okay, well, it's kind of difficult, I mean, with these points to draw some conclusion. And I think that's okay. There are many possibilities, but maybe the main reason for that, for this, the fact that these experiments were actually very difficult, is that if you look on the you have to control the microwave on the wideband, and if you look at the sample holder on the wideband, it's actually a microwave roller coaster. So essentially, you have depending on the frequency, and it can be you have many modes in the sample holder, and depending on the frequency, you will change completely the amplitude of the frequency drive on your system. That's one thing. But even worse, I mean, you can also change the way you drive the system. You can go from some driving of more one electrode and another electrode. So if you don't do an independent calibration of the microwave drive, I mean, it's going to be really hard to draw any conclusion about the universality. And so this is what we did in this experiment now, which I'm going to describe to you. So all these previous experiments were done in two-dimensional electron gas because they are very well-controlled systems. And in our case, what we did is to do this in single-wall carbon nanotubes. So this is a zoom on the layout, so you barely see the nanotube, which is here. There is a source drain bias, and you have a gate electrode. And we use one of these electrodes to convey the AC drive directly. So what you look at when you look at the conductance as a function of the two tuning parameters of the system, so the bias at DC and the position of the energy level, which is controlled by the gate voltage here. What you see here is that zero bias, you have a horizontal lines here. These horizontal lines, if you cut one of them, it's a peak. That's the Kondo resonance. And it's actually, it can be pretty narrow Kondo resonance, which will fit into the microwave range. And so we added a new, I mean, let's say a twist to the thing is that this guys now was embedded into a circuit QED architecture. And I think this is one of the reasons why we could, let's say, conduct this independent calibration, because let's say the microwave design was maybe slightly better, I mean, done than in these early works. But of course, we did this work a bit later. Okay, so so how do we do the microwave calibration? That's a very important step. So the idea is that we use the system as its own detector, but in a different transport regime. In fact, we go to a regime where we have a more traditional Coulomb blockade, where we have essentially a very nonlinear transport. And this very nonlinearity can be approximated to a great extent in some regions by a diode, essentially by some behavior. And essentially, this quadratic term in the IV curve allows you to directly measure the microwave power, which arrives directly at the sample. And this is why, I mean, and so that's crucial to do that, because you cannot, so you really have to do an in situ calibration if you want to have a reliable calibration. And if you do this, and as a function of the power which you shine onto the device, you see some linear regression here for the DC current which you measure. This is a direct calibration of the power on the system. And if you do this on the wideband, you see that, let's say the off state is when you shine no microwaves, and the on state is when you shine microwaves, and you see that this is a pretty flat response here on this side here, on this where here you don't expect to have any frequency dependent response. So this allows us like this to do an independent calibration between 1 gigahertz and 20 gigahertz. Yeah. Yeah.
Without any microwaves?
Yes. No, we don't have to worry about heating, because still it corresponds to very, very small power. Absolutely. But let's say that's a good point. So we a priori worry about heating, but then when we did the calibration, we found that the power was too small. So it was really small, so we don't have any electronic heating. So, and this allows us to have a calibration between 1 gigahertz and 20 years, which is exactly what we needed for this work. Okay, so let's first shine microwaves. So now essentially the AC amplitude, it's an absolute AC amplitude right now. What I'm showing now are plots with the amplitude which is known now with its absolute value. So maybe up to like 10 to 20%. So these are real values, I mean, on the device. So here is there are two examples here now. What happens? So this you see, you recognize here that's a Kondo peak here. So the highest Kondo peak is at essentially a very weak microwave drive, and you see that when you have a frequency which is low essentially, so comparable essentially, but to the Kondo temperature, which is about 8 gigahertz. So the frequency is 12 gigahertz. What we see is what we essentially see that some splitting, some apparent splitting of the resonance. So that's just an adiabatic modulation. That's a swing effect, right? If you take a picture of a swing with a long time pose, you will see the two maxima like this. But now what happens when you crank up the frequency? So at 19 gigahertz, what you see is that you don't have a splitting. You see, you have two peaks here, which essentially span, let's say, some decent amplitude window. And in fact, if you look the green curve here, you see that which corresponds to a cut here. You have 3 peaks occurring. So of course, you still, I mean, decrease the central peak here, but you have 2 satellite peaks exactly at the frequency of the microwaves showing up at this for this frequency. So, but that's okay. That's not new. I mean, it was already observed, but this is good to see this in a different system. So that's and so we again observe. I mean, satellite peaks for frequency, which is much larger than the or like reasonably larger than the Kondo temperature. But now what we're interested in is, which was not investigated so far, is the evolution of the Kondo peak in power and in frequency, because now we have an independent calibration for the power. And so it's just not that we did things experimentally right, but it's now we can really test thoroughly the theory of the AC Kondo effect. And this is what we have. So here is the map now of the conductance normalized by the conductance in absence of microwaves as a function of the frequency and the AC amplitude. So both these are normalized by the Kondo temperature. And here, that's the theory which is not directly taken from the paper by Kaminsky, Nazarov, and Glasman because they could study only limiting cases. So we found an ansatz which somehow interpolates between these all the limiting cases. So high power, low frequency, high frequency, low power, etc. And this is the theory. And in order to better show that we have a quantitative agreement with the ansatz which interpolates the theory, I have plotted to you 2 cuts here, which are along these arrows here, here and here and here and here. And so you see that in the dots are the experiments, and the continuous lines are in colors are the theory from the ansatz. And so all this map is qualitatively understood with a single fitting parameter, which is this A parameter, which is a parameter which is of order of 1 in the theory. So we do have a quantitative understanding of the of this data by interpolating the theory of Kaminsky, Nazarov, Glasman. So this can be considered as like the first and direct experimental test of the theory of the AC Kondo effect. Okay. So what about scaling now? Because of course, now you see that I have plotted everything with respect to by TK. So that's so now. Is it possible to see that everything is just expressed like that? I mean, well, it is possible if we study another Kondo resonance. But before that, I have not emphasized enough that you see here, we are at fixed power here, so the VAC is constant, and we increase the frequency. And you see that the Kondo resonance here goes up now. There is a more or less linear increase of the Kondo peak as a function of photon frequency. So this is fully predicted by the theory, but this is completely counterintuitive, if like at first sight. Because what we would expect is that if we have put a large frequency, you will destroy more the Kondo effect, because you will have higher energy excited states. So how can we understand this? So it's in fact built like some kind of like inside. I mean, it's inside of this theory. But can we bring like a picture of that? And here is the picture. So here is the setup. Now we have an AC drive, and in fact, this AC drive, since it is acting on the bias, it can be related to a phase, let's say, which is essentially a time-dependent phase, which fills the wave function of the excitations from when they go from the left to the right. And this time-dependent phase is just the integral of this AC drive. So what does this mean is that you have some kind of averaging effect. So the fastest the drive, the lowest the amplitude of this phase term will be, because it's just the integral, right? And in fact, if now you look at what this guy is doing to the Kondo cloud, it actually tries to bring, with a rate which we call gamma E, the Kondo cloud, which is a perfectly screened state, to an excited state where you have no perfect screening. And in this case, you have a large conductance. In this case, you essentially destroy, let's say, the conductance for a very small time. In fact, it can be considered as essentially a zero conductance state where you have an unscreened completely spin. Okay. And so, of course, the system tries to bring back, the Kondo cloud into equilibrium with a rate which is not just given by the Kondo temperature. And now, if you look at what would be, let's say, so in some kind of a sketch, the conductance as a function of time, essentially for a very high gamma E rate, you will have mostly, you will have a lot of times a zero conductance state, and for a very small gamma E rate, you will have most of the time a high conductance state. But this gamma E rate is just inversely proportional to the frequency, just because of this averaging effect of the phase of channeling of the excitations. And so if you just now, look at the average conductance by comparing the rates, you find indeed, in fact, this is a formula which is actually allows you to recover with this heuristically, the formulae of the full theory, which indeed tells you that the higher the frequency, the lower the effect will be on the Kondo cloud. Okay. So let's look at the scaling now. And for the scaling, we took, this was the narrow resonance which I explained to you, which we used previously. And we have another resonance which is much broader, on which we would expect that to have a different effect, because, as I told you, you have to rescale all the physical quantities by the Kondo temperature to see whether you have scaling or not. So this is what we did. And in fact, in amplitude, what you see is that although they have different widths, these resonances, when you rescale the AC power now, which is again is absolute by the TK, you see that the curves, the power dependence for this Kondo resonance and this Kondo resonance, they collapse on the same plot, which is again quantitatively understood by the theory. And okay, for the frequency, it's since it's a much larger Kondo temperature, and so even the span of 20 gigahertz which we have becomes small. Of course, we have less points, so we can only say that this is consistent with scaling as a function of f over tk. But nevertheless, at least the level is right. It's exactly where we would expect it to be for the conductance plots. Okay, so. So here is for the what happens when we drive the system with a large frequency. So we have a good agreement with the theory of the AC Kondo effect, even for the scaling analysis. Okay, but now for the last 6 minutes, I'm going to explain you what happens now when we try to read out this kind of many-body state with a cavity. Using the spirit of the cavity QED setup, which was explained, I mean, in his lectures by Mike. So, and the question which we're asking to ourselves is it possible to observe the freezing out of the charge dynamics in the Kondo regime? So the setup is very similar to what I explained to you, except that we will now, I mean, look at not only as, so we will not shine a large power AC drive on the Kondo cloud, we will just apply a DC bias in a linear regime, just to reveal the Kondo peak, and look at the transmission of the microwave signal between the left port and the right port of the microwave cavity. And essentially, we will measure simultaneously the conductance and the microwave response and see whether we can learn from that what I told you. So the cavity photons here are very interesting probes because essentially they mold the electronic gas and they test how much the gas responds to an increase or decrease of a chemical potential. In other words, I mean, it's a direct way of measuring the compressibility of the electronic system, and the compressibility is very sensitive to correlation effects. So, so in order to establish a common vocabulary, it's interesting to see more accurately what the resonator probes. And for linear response argument, you can see that by looking at the transmission of the cavity, essentially the compressibility, which is the zero frequency charge susceptibility, shows up here in the denominator and essentially provides a shift, because it's real here, of the frequency of the microwave cavity. And by looking at how this guy shifts the frequency of the microwave cavity, so this can be directly measured by looking at the phase of the transmitted microwave signal, you have a direct access to the compressibility of the system. So, well, let's take another. So this is a different single-wall carbon nanotube sample where we had Coulomb blockade regime for 1 gate range. So in this, what we saw is essentially Coulomb peaks here. So each time we have resonance between one charge state in the leads. And essentially we have peaks in the conductance as a function of the gate voltage, which controls the position of the energy levels. And we have perfectly correlated peaks in the phase of the transmitted microwave signal, which is just a perfect correlation between the compressibility and the Coulomb peaks. That's normal because these peaks occur when we have these green levels in resonance with the Fermi energy of the reservoirs. So this allows us to show, in fact, that the two systems are actually coupled, very well coupled. So the coupling strength is about 100 megahertz. And this corresponds to a tiny charge sensitivity. It corresponds, so this kind of phase here, the phase noise here can be mapped onto a charge sensitivity of 2 × 10⁻⁴ electrons integrated over the bandwidth. So the electrons and photonic systems are well coupled together. What happens in the Kondo regime? And this is what happens in the Kondo regime. So again, now we have, now we just crank up the gate voltage. And by doing this, we not only move the energy levels, but we also change the tunnel barriers and open more the tunnel barriers. And this is the situation where the Kondo physics will show up because we have a larger coupling with the electronic continua. So you see here ridges here, and if I do a cut here, I see a Kondo peak with big bumps here. These are the big charge peaks. And if I look at the microwave signal, I see that the microwave signal is completely insensitive to this peak here. So the Kondo resonance is completely transparent to the cavity photons. And that's a direct illustration of the separation of the spin and charge degrees of freedom in a Kondo system. And this is very well accounted by the numerical renormalization group done by Min-Chul Lee and Man-Soo Choi. So we can look at the temperature dependence, similar things, one can conclude similar things. And so this measurement is the direct observation of the freezing of charge dynamics in the Kondo cloud. Okay, and if you want to ask me, questions more about this, we can develop this more because I'm running out of time. But let's now put this in a wider context. So now you see that I have a strongly correlated system, which is this guy here, which is now coupled to cavity photons. So I have a hybrid fermion boson system. And so this is why, I mean, by doing the analogy between the photons in the cavity and, for example, an Einstein mode for phonons in solids, we like to see this as like a basic circuit for doing quantum simulation of fermion boson problems. Okay, So in conclusion, I have shown you that we have done an experimental test of the theory of the AC Kondo problem, which has led us to observe a counterintuitive microwave Kondo enhancement, and also the scaling laws, essentially, of the Kondo problem at a large frequency. And in the second part of the talk, I have shown you that shining light can be also interesting to probe many body systems. And this has led us to observe like the freezing of charge dynamics in the Kondo resonance. So the perspective of this sets up, since we did like photon-assisted somehow tunneling in a many-body system with a classical field, and we have a cavity, and Mike has shown you that in cavities, that if you have nonlinearities, you can make non-classical states of light. Of course, you can. The natural thing is to try to bridge the two things together and to try to learn even more by using, like looking at photon-assisted tunneling with non-classical light, and along the lines of a paper by Ash, some time ago. And we like also to like in same spirit, we could imagine to populate with a large number of photons the cavity and to look at quantum quench of the Kondo cloud. And this I've talked to you about this. Thank you for your attention.
Questions? I was curious on the theory side. I mean, are there any kind of analytic computations of the scaling functions in this AC case? So you saw the scaling collapse, but are there predictions for the actual functional form?
Yeah. There are predictions in limiting cases, and so which is in this paper by Kaminsky, Nazarov, and Glassman. In the full crossover, I don't think there are theoretical predictions, and this is why we had to rely on this ansatz here. So this ansatz is an analytical formula which spans the whole range, also the crossover, but though there is no decision interpolation, a smooth interpolation. So the limiting cases are fully analytical, but the like the crossover, there is no, I think, analytical formula for the crossover, to my knowledge.
So Takis, the suppression of the main Kondo resonance with the AC voltage amplitude, wouldn't you get something similar just with ordinary photon-assisted tunneling? So a non-interacting resonance, this Bessel function, like can you tell the difference from just that simpler setting?
So so the difference, I would say that it is it's I would say the scaling of so the functional form of the scaling would be different, I think, but this is true that the suppression is.
So it'd be quadratic with the voltage as well.
Yeah.
Right?
So that's and the prefactors are also different. But I think that you're right. So the general feature qualitative. That is why it's important to have a calibration of the power. It's definitely like there are some similarities with the photon-assisted tunneling. You're right.
Questions? Actually, I was curious as to whether there is any kind of similarities in kind of the broader picture with things like the Cavalieri experiments, where you're kind of trying to see kind of transitions to kind of superconductivity by driving kind of vibrational degrees of freedom. Here you've got an electronic system that you're coupling to photons, and you're somehow kind of changing the kind of intrinsic dynamics, and maybe you can see kind of photon-driven phase transitions in these systems.
Oh yes, thank you for this very interesting question. I think that, yeah, you can, so that's a bit, but that's not exactly a bit this, no, sorry, that was, in fact, some kind of the secret purpose of this line here. In fact, you're right. If you do the analogy between the photons and the phonons, you see that, for example, you can have some interaction mediated by the photons. But now the phonons themselves, they're there, right? You don't really control them. They're there. And here you could imagine to do something to the photons, to engineer some kind of interaction which would not exist, for example, would be difficult to unravel in a real condensed matter problem. I have no example. So I think there are some theoretical works devoted to this problem or to enhance. So I know I don't know exactly. I don't remember the reference, but some kind of enhanced superconductivity for this kind of cavity setup with a 2D electron gas. But I think this is the idea what you say, right? So you you can change the kind of way of the electronic state interact, and thanks to the cavity mode. But here, with the tool that you can do things directly to the cavity mode, as exactly Mike showed. I mean, you can use the whole machinery of quantum optics to engineer the cavity mode, and maybe you can get into a very interesting new, quantum phase transitions. Yeah.
Any other questions? Okay. Well, if not, let's thank Takis for a very nice talk.
Thank you.